Welcome, everyone. Thank you very much for signing on onto our special interest group, History of Operations Research in South Africa this evening. Usually we have speakers who are lifelong members of ORSSA. But this evening we have a bit of change. We have Quintin and Marno. Now they're not quite retired yet, so they are not yet lifelong members of ORSSA. But I don't know whether you all are aware of that, but both of them were part of the authors of our book on history on operations research in South Africa, the first 50 years. They co-authored the chapter on simulation. And that's why we invited them to come and talk to us about simulation on the special interest group of history of operations research in South Africa. Now, you will see from the theme of the talk, it's from the humble beginnings of simulation to artificial intelligence horizons. So we're very looking forward to this journey, but let me just introduce our two speakers. It's Quintin van Heerden. He's an industrial engineer and he has more than 30 years experience. He began his career as a transport modeler specializing in large-scale agent-based freight models. Quintin then spent a decade in the CSIR's Logistics and Spatial Planning Group, leading initiatives including the development of Africa's first cloud-based urban simulation platform. Quintin then led the data science and engineering team at Enhanced Supply Chain Solutions, and currently he serves as an operations research engineer at BASH. He earned his PhD in industrial engineering from Stellenbosch University, and he developed, as part of his thesis, a distributed simulation optimization system in which meteoristics autonomously guide urban simulation models to attempt to achieve predefined aspiration levels. Quintin, I would like to see what is the exact title of that. It's quite long. He previously served as ORSSA's Pretoria chapter chairperson and SIG's Operations Research Special Interest Group Portfolio Manager. Welcome, Quintin. Then we also have Marno du Plessis. He's a data scientist and operations researcher at Discovery Limited currently, with over 5 years of experience specializing in optimization and generative artificial intelligence projects, primarily within the contact center domain. Marno holds a master's degree in industrial engineering, also from Stellenbosch University, and he was awarded University Medal for the top magister student in engineering for his thesis on using reinforcement learning to develop inventory management policies in information sharing pharmaceutical supply chains. Marno also served as the head, and he currently also serves as the head of member relations at the ORSSA Executive Committee. Welcome, Marno. And with that, I hand over to our speakers. I don't know who of you are first.
I will lead us into it. Thank you so much for the introduction, Marthi. And good evening to all. Thank you for joining this evening. It's really good to see some familiar faces here and not so familiar yet. So welcome to all. Alrighty, let's jump into it. So have you ever wondered if this is real life or if we're just living in a simulation? Or do you ever look at someone, something, maybe a complex system, game, thing in life, and wonder what on earth is going on here? How does this work? Well, there are various phenomena around us and complex systems around us, and it's not always so obvious how they work or even why they work. All right, so today in this talk, we'll do a brief introduction to simulation. We'll touch a bit on simulation history, tracing it back all the way to its roots. We'll talk a bit about simulation paradigms and the software used in simulation, touch on some case studies, publications, and examples. And then we'll talk a bit about how and where the buzzword AI or artificial intelligence fits in, and then how we can take lessons from history into the future and how it will guide us going forward. So, when you hear this word simulation, what's the first thing that comes to mind? I'll just briefly give like 1 or 2, 3 seconds. Think about what it means to you. Um, you're welcome to post in the chat as well as we go along, and we'll have a look there as well. Maybe you didn't realize that you were using it in some way or another. So think a bit about emulators to test mobile applications or API testing in software like Postman, Bruno, Hopscotch, those kind of things. Perhaps emulators playing old games on old devices, but now on a new device that has an emulator on it. Or if you use virtual reality headsets or digital twins of cities, like all of these could be regarded in some way or another as a simulation. But if we take a look then at the actual definition of simulation, it's basically the imitation of some situation or process, or it's a computer model of something. And if we zoom into the word model then and have a look at the definition of a model, it's typically a representation of something, typically on a smaller scale than the original thing. So it's used as an example or some representation of something. So what does simulation then entail and why do we use it? To summarize basically all of that, it's an imitation of something, it's a simplified version of something, and it helps us really gain insights into emergent patterns that aren't necessarily obvious at the time of observation. It also helps us understand the complex interplays between various things, and it helps shape our understanding of the world around us. And then, for those of you that are not familiar with ORSSA, it's the Operations Research Society of South Africa, and they also champion this through advancing operations research in South Africa.
Thanks, Quintin. And yeah, I think just to say, you can raise a virtual hand at any point if you would like to make a comment or ask a question, and we can take those as we go along. So as the youngest member of us two, I've got an enviable task about talking about the history of simulation, but I think that's why someone like Dave Evans can also help us out where we go wrong. So if you talk about history of simulation, then typically you can think of it like in two parts, where the one is pre-computer era, and I think for most people then really thinking about computer simulation itself is much more of a familiar concept. You can really imagine what that looks like, but what would a pre-computer era simulation look like? So there can also be some debate depending on what your exact definition of simulation is, whether you regard this as real simulation or not. But typically in literature, we will go back as far as 1777. So Quintin, if you can bring up that first part of our slide, please. So there's this very famous experiment called Buffon's needle experiment. So because we are somewhat nerdy, I'll explain what happened, but don't like quote me on the maths. But what happens here, and I think maybe just my own experience of this is like you do something completely wacky to get to some other funky maths estimate or something. So it doesn't really make sense, but in the end we get there. So what happens here is if you look at the top half of the picture, we've got these parallel grid lines, let's say, and they're all equal distance from one another. And then we have a bunch of needles, and then each needle would have a length shorter than the width between any two bars. Um, and then obviously there's a lot of math behind that, but it so happens that when you now drop these needles randomly onto this, let's call it surface or plane, then naturally some needles will cross a line and some won't. And then if you were to take the ratio of the needles that crossed the lines over the total number of needles thrown, then you will find that this approximates the constant pi quite well. Now, sort of why we can relate this to the concept of simulation is we've got randomness involved. You also repeat this process many times. So what the bottom graph depicts is the more estimations or the more needles we throw, the more accurately we can approximate this value, right? So if we only do this experiment once with maybe 10 needles in total, then we won't be very accurate. But as we go further and further and further, we get closer to that 3.14, and then however many digits you can memorize. So that's quite an interesting, something you can do to simulate this physical process of throwing needles onto something to estimate the constant pi. So that happened then a couple of centuries ago. And then something slightly more recent, which is then also features as the start of talking about simulation and simulation methods, would then be Monte Carlo simulation, which I think around the 1930s probably really came to the fore. And what happens in this case, and spoiler, it's again an approximation of pi. So again, I'll give a quick nerdy explanation of what's happening here. So we have a square, and then if your eyes are still good, you will see that it's like the length of a square is unit 1. So the surface area of the square is 1 by 1, so only the number 1. And then obviously we've got a quarter circle here, and the area of the circle would be, so we know the area for a full circle would be pi times radius squared. And then because we're only dealing with a quarter here, the surface of that quarter circle would be pi over 4, because the radius in this case is 1 also. So, I mean, if you didn't follow all of that, my apologies. But all in all, what it boils down to is if we take the ratio of the area of the circle part over the square, that is like approximated by the pi over 4, which would then be approximated by the number of red dots over the total number of dots we see here. So essentially it's the surface area of the quarter circle over the surface area of the square. That ratio would approximate pi. And then how you would do it is, it's like maybe a couple of different methods, but in this visualization is we can imagine we've got this square on some plane or surface, and then you can just imagine randomly, or let's say at least uniformly, dropping little balls or spots onto the surface. So, and then you would just mark, does it fall within the circle? Then it's the red dots. If it's outside, then it's the blue circles, and then just the ratio of red dots over red plus blue dots would approximate pi. Okay, so that was a long story about like pre-computer era. Now, when it comes to the more formal history of simulation, I mean, it's probably not the most riveting part of the presentation, but I think to be true to, I think where we come from with this talk is just to tell everyone that if we think about simulation and more closely than computer simulation, people would trace it back to like the World War II era, although you don't necessarily get too much agreement in the literature. But, let's say the 1930s, 40s, with most of the like pioneering work in the 50s and 60s. So sort of quite famous is Jeffrey Gordon from IBM, who invented the first simulation software package, so general purpose simulation system, GPSS. And I think, as all of us can imagine, 60, 70 years ago from today, in terms of computers, obviously lots of storage limitations, very slow, very expensive. And then at the time, simulation was quite an exclusive endeavor, right? So not only was it new, but even if you wanted to try it out, you would have really needed the capital to build, or well, let's say, acquire the hardware to build and perform these simulations. So therefore, it was typically only done by the large companies, and usually in steel and aerospace industries. And then another sort of hindrance to the real expansion of simulation was just the scarcity of published literature. So you can't really find any studies or things to leverage when you want to do your own simulation. So that's just a bit of an obstacle in the expansion of simulation. And then there's also this famous story of one Julian Rietman, who was one of the first people to use GPSS on an IBM 650 computer, which I'll show a little picture of on the next slide. So he had some queuing problem, which couldn't be solved with an analytical method. So someone said, well, let's try this simulation thing. And then I'm not quite sure how long it took, but I suppose it took like weeks on end maybe. So it just exceeded budget and time constraints. Really needed a lot of people. And then in the end, he called the results ambiguous. Although I'm not quite sure in what sense that was. But all in all, so in this period, some people then also called simulation a method of last resort, just because it wasn't as practical or feasible to really go about it. So in terms of IBM 650, I thought I'll just I think show some of us what that looks like, and I think you'll do well if you've ever seen one in person. Now, this thing I think weighs about 2.5 tons, and I think it has a memory equivalent of 35, so that's 35 kilobytes. So I mean that's fairly small, I'll imagine. But yeah, so that's just a picture of what that beast looks like. And then the other part of this slide is just to show you what this GPSS sort of would look like. So that middle part there, the block diagram. So that we would typically talk of this block diagram language that you would use in this GPSS. And then in this example, there's like this barbershop, let's say, problem or model, which is sort of the equivalent of the Hello World, which I think most of us would have heard about. So maybe just for some context, maybe if you're not too familiar, give you some idea. So we would start off with the generate block right there at the top. So customers would arrive into the barbershop. Then it's a bit small, but there's an 18 and a comma and a 6. And that would then refer to some probability distribution where I think the mean is 18, and then some standard deviation of something of 6. And that would then be the rate at which customers arrive. They would enter the queue. The facility's name is Joe for some reason. But yeah, and then you can model this process of people waiting in line, getting their hair cut, moving sort of out of the chair, exiting the shop, and so forth. And then this picture on the right-hand side, which again, maybe a couple of those on the call might have used in their lifetime, but it's like a punch card on which this problem would have been modeled, simulated on. So I think, I mean, I have no idea really what those are, but I think it just gives us some idea of where all of this started. And then as we go through the talk, you'll see some more of where we are at today. Okay, so some history, and then a little bit more recent is just catching up on Mr. Rietman. So a couple of years later, he like simulated some new problem again, and he got results within 6 weeks. And then turns out he was quite happy with that. And then obviously as computers further advanced, like the visual capabilities also came to the fore. So interest in animation increased. And then maybe just again, simulation adoption was quite slow generally. But then here from 1980s, 1990s onwards, when computing power was much more readily accessible, cheaper, we had the animation capabilities. Also compatibility with other software was quite big. And then we can say really simulation entered into its maturity phase from the 1990s onwards and all the way through to where we are today.
Great. If we then take that and try to summarize the different types of simulation or simulation paradigms into like distinct categories, there's 4 themes that we'd like to highlight in this talk. So first of all, we have agent-based modeling. Here, the key characteristics are that you have agents that represent entities or someone or something that needs to make decisions. And they typically have attributes and they can interact with one another or the environment. They are normally goal-driven or utility function based, and what that just generally means is that they learn through experience. And there's some function that you have to provide it to know how it scores a certain thing that it does. So typical applications here are in transport modeling, urban growth modeling, ecological simulation, and supply chain. As an example, let's say for a transport simulation, an agent needs to travel from his home to work. He needs to decide what time to leave. In the morning, he leaves too late, gets stuck in traffic, and that's a bad thing, arrives late at work. So typically in this case, a utility function would score negatively, and then the agent would learn no, he needs to leave earlier the next day, so he adapts. The next morning he leaves earlier, gets to work on time, and that is then seen as a positive utility. And that way the agent learns what is deemed the right behavior. Then if we move on to discrete simulation, there we have systems that are modeled typically as discrete events over time. You have event scheduling, you have state changes, and you have distinct transitions between these different states. So here, think about a manufacturing plant, for instance. You have an item that arrives, a resource processes it, and the output goes onto a queue for processing downstream, as an example. Then we go over into systems dynamics. So here it's more of a continuous system. So it's continuous changes that get modeled with feedback loops between different entities. So you typically find things like stock and flow diagrams. So they represent the complete system. And then the idea out of this all is to, over a longer term, start to see emergent behaviors that aren't necessarily obvious at that time. So yeah, typical applications in resource management, business forecasting, and population growth modeling. Maybe another example is something like a bank account with payments into and out of the bank account, and then you earn interest on the balance, and that continuously updates as time goes on. And then in the last category, we have hybrid approaches, and the main crux of it is that you want to combine different approaches to get the best of both worlds. So not only do you get the complexity, for instance, out of your agent-based simulation model, but you can couple it with an optimization algorithm to then optimize certain parts thereof. So typically simulation optimization or simulation-based optimization. Or you could, for instance, combine system dynamics with agent-based modeling or cellular automata even, which in itself could be seen either as discrete event or agent-based, whichever way you model it. There, your typical applications are in healthcare systems, environmental policy planning, and urban systems policy planning, and there could be many more, of course. As an example, on the AnyLogic website, actually, there's a real nice case study around some hybrid approaches. And this is just one example of where the case study ingested data from SAP into a simulation model that simulated the supply chain network. And then on the output side, the output data gets converted into the metrics that are used for analytics. But then they plug in a linear optimization model to go and optimize some component of the simulation model, which is an interesting hybrid technique that one can use. Another example, maybe drawing from my own PhD work, is where I used an urban simulation model to predict how a city will evolve into the future, and then coupled onto that a meta heuristic that generates sets of problems to be tested in the simulation environment. And then the meta heuristic learns from the output indicators and then guides itself to try and achieve some predefined aspiration level. And here the cool thing about it is that you could actually spin up multiple simulations in parallel. You can distribute that onto like a high performance cluster, and you could couple to it some meta heuristic that guides all of this to eventually achieve some outcome, which should be then evident how this is much more powerful than just using a normal simulation model. So in terms of the typical software that's used in simulation, again, per category. There's many other packages also that get used, but these are among some of the more notorious ones. So AnyLogic is very well known across all the different types of simulation, and it's very good to do hybrid simulations as well. In the agent-based category, maybe to highlight, UrbanSim is for urban growth modeling, and MatSim is a really large-scale traffic transportation or transportation simulation modeling platform. On the discrete event side, there's some of us, I think, Rion, you would also attest to when we were at university using Arena initially, and then switching over into Simio later on, and Simulate's also come along in the meantime. And an interesting one is Bazaji, which is typically used for business process modeling, which we categorize here as discrete event, but it's essentially taking your business process models and converting them into a simulation model so that you can test the effects of certain policies within your business processes. On the systems dynamics side, I guess Stella is the standout or the most notorious package actually. And then in terms of hybrid approaches, what you normally see is that that case studies often involve some simulation package with some programming language. Like the example again out of my PhD, it's a Python-based solution where you have a custom meta heuristic or some custom algorithm that you or model that you develop that you couple then with your simulation package.
Right. So as part of the history of simulation, what we've done when we written this chapter for the book is we spend a good few hours or days like combing through all the papers presented at almost 50 ORSSA conferences, and we also looked at papers published in Orion, which is ORSSA's journal, and we went to pick out all the studies related to simulation, and we included little descriptions of them in the book. This book was published in 2019, so essentially the time period we had for this particular analysis or summary was then up until 2018, with the very first simulation-related paper appearing in 1973. So we just wanted to give you some idea of what people in ORSSA were studying or doing with simulation. So the table on the left-hand side is really just a loose categorization of different topics or categories of simulation studies performed over the years, and then also split into the different simulation modeling paradigms that Quintin has highlighted. Now, I think some of you sort of might know or be familiar with lots of simulations, especially surrounding the world of logistics. So if you look at logistics, you can see a total of 27 studies there relating to logistics. So that would typically include your supply chain modeling. So we can model some supply chain network. That means we can model how many suppliers do I have, how many customers do I have, what are my lead times between different facilities, and then I can simulate different scenarios. So what if I have a stock out at facility X, what would happen? So quite a popular application. And then also discrete event simulation, making a lot of sense in that particular topic. Then manufacturing and production related topics also quite popular. And then also just on the paradigms again, so discrete event simulation is one of the older ones. So you can see there a total of 41 of the 77 studies that we've looked at involved discrete event simulation, with agent-based modeling really gaining traction more recently. And the graph on the right-hand side would just show the increase in simulation studies that were published already at conferences. And I think it also makes sense for this graph to like really spike up in the latter years, just as simulation became all the more pronounced and also, I think, accessible. But yeah, so I mean, we would obviously argue for go read the book to get more information, but I'll just spoil you with a couple of specifics on the papers that were published. So yeah, there was one in 1985 on residential planning in Richards Bay. In 1993, we had one where the let's say runner congestion at the finish line of the Two Oceans Marathon were modeled. So this was like a project coming from the Two Oceans race organizers themselves. So they were trying to, I think, look at once runners cross the finish line, and I think they need to sort of, I don't know, queue somewhere. What would that congestion look like? So that was one of it. Then you also get something quite unique, like modeling the role of theft in plant conservation. So that's quite an interesting one. And then also disease modeling, quite a popular one, which brings us to this particular slide, which is again just some higher level categories of simulation, which I think maybe we sort of know it, or maybe we think of it, but we don't really understand the power that simulation gives us for modeling these particular things. So like Formula One car design, or I think this will hold true for many different vehicle designs, or even bicycles in road cycling. So obviously, if we are, let's say, Mercedes, then maybe we can build 1,000 cars with all the money we have, but we're not going to build 1,000 cars and then just drive them around the track to try and get data on how is our car performing in the wind, because that obviously costs a lot of money to just build 1,000 cars for testing. And also, we can never go and drive our car around the track under all the different situations or circumstances that we want to test it in, right? So if the wind is only ever going to blow from the easterly direction where I live, then we'll never get an idea of how does the car perform when the wind blows from a northerly direction. So yeah, simulation really comes to the fore. So we can simulate, or let's say we design our car, and then we can simulate all kinds of different situations. So as this little picture would suggest is, let's say you are racing and we look at the air pressure, which parts of the car are affected more than others, what does that do to the drag resistance, and so forth. So we can model all these different kinds of scenarios and make sure we get the fastest car out of it afterwards. Then Quintin also touched on the topic of urban design. So again, this picture, which looks a bit abstract now that I look at it again, it just models well, actually what it shows is how wind would, let's say, blow through a city. So if we think of building a new building in a city, then we can also look at what effect would that have on the wind in and around the streets, let's say, in that building. We can also, there are even some simulation models I've seen where you've got your city and you can model what would happen if a bomb were to explode at this particular location, and you can have some idea of potential impact on buildings, people, however busy that part of a city may be. And then up until like really modeling the expansion of cities, more people moving to your city, more houses, buildings, what does that do to traffic, and so forth and so forth. So really many applications there. Then again, just on the car front, so like a crash testing one. So I think we're all quite familiar with the concept of crash test dummies, which you can take your car and drive it into a wall. But if we can do it with computers, we can save some resources, test more, different permutations. So there's one. Then climate modeling. So again, we all know what's happening with climate change. And now we also need to ask questions, but maybe how do we prepare, or how do we educate ourselves on the possible scenarios going into the future? So I suppose this is quite a difficult thing to do, but if we can build a simulation model that can model the climate dynamics at some level, we can also simulate different, let's say, weather patterns, right? So if we can simulate what would happen if there's more rain or less rain in this particular area of the world. What would happen if some average temperature rises by 1% every year for 10 years, and get some idea of what will happen over time under different circumstances. Something like passenger flow in an airport, so also extends to many other places where you've got people moving around. And also somewhat similar to the two oceans example I just mentioned. So we've got lots of flights coming in at certain times of day. That means plenty of passengers coming through our terminals. What does that mean for how many terminals maybe should be open? How many staff should we have? We would need more when there are more flights coming in, maybe less so when there are fewer flights, that kind of a thing. And then also disease modeling, I think quite a popular one as well. I think especially during COVID times, these were quite relevant. And I see Sheetal is here, like she can tell us more about that if she want to, but also quite powerful in, I think at the time, giving some recommendations or advice to government and saying, listen, we can model this COVID disease. Yes, we don't know too much about it, but we can model some scenarios or permutations and tell you that, listen, in the worst case scenario, we think this is what it's going to look like. So if we look at mitigation strategies, then we can suggest X or Y or Z. Yeah, so that's just, again, I think to maybe broaden your mind a little bit on what is really possible with simulation, because I think if you are not too familiar with it, then you're sort of stuck with, well, I don't really know where I can use it, but maybe it, I think, stretches your mind and you can already think of applications of it for your own personal life, even if you don't think of yourself as some scientist or operations researcher.
Great. So any presentation in 2025 that does not contain AI is incomplete. So where does the buzzword AI fit into all of this? We'd like to kind of distinguish between two schools of thought here. First of all, we have AI assisted or like co-pilot development. So here it's the use of artificial intelligence to really enhance or streamline your development process. Think about this as a way to augment or extend or inform your development workflow. So in short, you're using AI to do your model development. And then on the other hand, you have agentic workflows and systems. And here it is a complete autonomous system that you enable to make decisions or achieve actions independently without necessarily supervising. And here, very much like you have in agent-based modeling, the agents or AI system is trying to achieve some specific goal. So what does this mean for us in terms of simulation? I've tried to kind of compile for us a couple of examples and case studies and some concepts that we can talk a bit about with regards to AI and how it fits into the simulation paradigm. So found this really interesting study where researchers used a generative AI approach to try and mimic user behavior. So what they essentially did was they took interview transcripts of a couple of people and then fed all of that information to an LLM. The LLM was trained on that extra data and they tried to then simulate people's responses to survey questions. And they actually obtained an 85% accuracy in how the agents responded to the questions in the survey, which is quite interesting. The second example here is a platform called HyperSim, which they dubbed themselves as a true agentic simulation platform that automates like the whole STEM engineering lifecycle. So they claim that you can design, simulate, and validate your whole simulation process using interconnected AI agents. I think we going to start to move much more in this direction where you have a full agentic AI workflow system with which you can build out your simulation models. Then there was an interesting study around the use of LLMs or large language models to empower agent-based modeling. So essentially using these LLMs to provide a completely new perspective on reasoning. So in your agent-based modeling paradigms, normally your agents make decisions using some rules like we discussed earlier. So for instance, you would tell the agent that getting stuck in traffic is a bad thing, as an example. But here, the power of using LLMs is that you don't necessarily need to provide instructions to your agent anymore. So the agents can actually behave in in never before seen circumstances or scenarios. Whether that's a good thing or not, I'm not entirely sure yet, but it's an interesting approach. And then I think another benefit here is that agents actually communicate with one another using natural language then. So it obviously makes it easier for us humans to actually study that interaction as opposed to writing code. And then the last one here is what's called embodied AI. So NVIDIA is actually a very big player in this field. And the long and the short of it is actually that it's a way to get your artificial intelligence to interact with the real world. So I think Marno also touched on this earlier, but the concept is around that NVIDIA is using simulation to generate a lot of synthetic data, with which they then train their robots. So this helps them save a lot of time, actually reducing years and years of actual physical testing to just pure minutes, in which they can rapidly test new scenarios and actually learn from them, and then go and let the robots interact with the real world thereafter. Some of the concepts just coming out of artificial intelligence that we should not neglect here is be careful. AI and LLMs are prone to hallucinations. We often see that they produce plausible but very incorrect or factually incorrect results. And they could really be biased as well, depending on what training data was used to train them. They often also rely on patterns rather than actually true understanding of the situation. So coming back to the action without instruction, it could be a really dangerous thing. There's also the concept of model context protocol. So this is a fairly new protocol. It's an open standard. Here, the crux is that it's a way for you to connect your artificial intelligence models to external tools and data. So that's like the very simplistic definition thereof, but it really bridges that gap between your apps and your data. So think of it sort of as an API, but it's not really an API. Then there's also the concept of agent-to-agent protocols. So as we get agents that start to do things much more autonomously, we need a way for them to actually also communicate with one another. So here there's a new protocol or standard that's emerged, which helps them communicate with one another and discover one another, and also know what type of work they can request from one another. So you typically have what's called agent cards, which describes a specific agent, and then tasks, which is your request to do work. So one agent will request another agent to do some work, and it will respond with the result of the work. And then right to the end, we have agentic AI and orchestration. So much like you have in agent-based modeling, your agents that need to be orchestrated in some way, you still need to provide some level of guidance as to, as the one finishes with something, what should happen with the result. Here in your agentic AI world, it's very similar in the sense that you need to orchestrate everything. And I guess eventually that will all be autonomous as well. But AI agents also typically have goals that they try to achieve and then act accordingly. So an example perhaps of an agentic workflow found on the web. So here it's a user that requests a flight to be booked, and we can see actually a couple of different agents that handles this request. There's a booking agent, there's a calendar agent that checks for available flights and availability of the user, and there's a payment agent that will handle the payment part thereof. So each of those agents then need to perform the appropriate actions, and right at the end, all gets aggregated and finalized, and the only result that the user receives is the booking and payment is done. Your flight has been booked. I, again, am a bit weary of this fully autonomous way of doing things, but it does provide us with a glimpse into the future as to where we are heading, and it's happening fast.
Right. So speaking of fast, we are on our last slide over here. So yeah, just a quick overview of what we've covered. We've spoken about simulation, which let's say is about 100 years worth of history in the more formal sense of how we maybe define simulation. We saw it was very inefficient, expensive, slow right at the start. Part of that would be because 60 years ago we can't really capture the high degree of complexities we have in the real world within the sort of more primitive infrastructure that we had available. So that all changed, and then I think it is quite clear that we illustrated simulation is obviously safe, very versatile, cost effective. The visual part of it also makes it quite appealing to many people, even from the low-level developer to your executive in the corner office can also see this, and then also getting call it immediate feedback, but let's say relative to a simulation that ran for 6 weeks 50 years ago. I think even if you just run a model today for 2 hours, that is quite quick to get feedback, make a change to your design and test again. So yeah, this really just leads us to think of our responsibilities as OR practitioners. And even if you're on the call and you don't know what OR even stands for, then I think you can also call yourself one, because all of us, I think, needs to be responsible in how we go about, especially using something like a simulation. So the adage of garbage in, garbage out always applies with simulation models as well. So we need to validate and verify our models, right? So you can build something, you can say, oh, yes, I think this is a barbershop simulation, but if we miss some critical part to it, such as that the barber always uses the hairdryer for 3 minutes and not for 1 minute, it would obviously mess up your whole simulation. So we need to make sure that we keep true to the real world. And then I think Quintin touched on the idea of AI quite well now, but use AI with caution. We can't just let everything into the hands of an AI. And if we also think of operations research as the science of better, then I think the word science should still pull us back to first principles and what can we really do. Yeah, I think let's say with a more analytical kind of an angle, instead of just throwing something over the wall and say the AI would take care of it, which I think also means that we should continue using simulation as a decision support tool and not as a decision replacement tool. So I think it would still work well for humans to still look at results with their own eyes. And there's some, let's say, level of judgment that probably a human would almost always have over whatever result an AI can spit out, which obviously also means we should consider the ethical uses of simulation, especially as we get into this AI world that Quintin also referred to, where all of a sudden I don't have to build a physical robot to go and test how it will do in a warfare scenario. The robot can just live in a simulation and test a million different warfare scenarios just all by itself in a virtual world. And if we think about those kinds of things, obviously ethics also comes into play. But yeah, that is above our pay grades. So we thank you for listening to our talk. We hope you learned something if you didn't know something. And maybe in 60 years' time, Quintin and I will still be here and we will be lifelong members of ORSSA, and we can tell you how far simulation has come. So yeah, we thank you for listening, and then open the floor to any questions or comments from the audience. Thank you.
Can I chip in with a couple of comments?
Go for it, Dave.
Go ahead, Dave.
Okay, thanks. First of all, congratulations on an excellent talk. Very well done, the two of you. I've got to go back to your GPSS references. Back in those days, I had just joined ICI, which in England was the parent company of Atomic Explosives. They had the largest IBM mainframe in the country, and in those days, when you bought an IBM computer, you got all the software for free with it. So you got Fortran and COBOL and GPSS and a thing called CSMP, which was a systems dynamics package in Fortran, which was absolutely mind-boggling. It had macros and all kinds of things. GPSS was a foul simulation language. The only reason it got used was because it was free. There was a whole family of other Fortran-based packages which worked far, far better than GPSS did. And the guy I joined in ICI had written this continuous systems modeling package with IBM. He was a guy called Mike McCann. And my first job with it was to build a simulation of the biochemistry of a dog to study heart drugs. It was very simple, very simplified model of a dog, but that was my first job. Yeah, so there you go.
Thanks, Dave.
Thank you very much for that, Dave. I also want to do some little bit marketing here. If you want to look at Dave's presentation again, you're more than welcome to visit the YouTube channel of ORSSA or just read the blog. Dave was our first presenter on our history of operations research in South Africa, and I remember well that you referred to the simulation. Any more questions? I think I see there's some chats. Any questions from anyone else? David?
I have a question.
Yes,
Shita,
go ahead.
my hand's raised.
Yes, there I see your hand. Go ahead,
Yes.
Shita.
Good evening, everyone. Thanks so much for the talk today. I think my question was, I think in the world that we work in health, particular. I mean, I just came off a call today with SAGE, the strategic advisory group of experts, who make all the health policy for the world. And we use modeling, we use simulation, almost on a daily basis to support decision making on policies. And with with a hybrid, not necessarily a hybrid simulation models, but with simulation models now with that incorporate sort of elements of AI, I wonder to what degree validation is being improved. Sort of methods for validation are being sort of emphasized as quickly as these sort of new innovations in AI are being developed. And I wonder if anyone on the panel had any insight into validation, or is the world getting sort of so what is the word, excited, perhaps, or hypnotized by the fast pace at which new methods are developing, that we're forgetting the part about, or the part about checking them is being left behind. Thanks.
Hi guys, thanks.
Quintin?
Oh, sorry, I was going to just quickly, what Shital was saying about validation, and I think verification as well. I mean, the simulation and the AI fields seem to almost have similar sort of theoretical problems in that they're both very nice tools to use, and they often made accessible to users who normally wouldn't be exposed to such sophisticated kind of mathematical modeling techniques, because they've got quite nice interfaces, they're very visual, people can play with them. But this idea of trying to understand better how we understand both the verification and the validation of these systems, both the AI systems and the simulation systems, I think is a particularly hard challenge. And as we use them more, and we take their results more seriously, and the results have more consequence, it seems like this is a very interesting field to work in. Thanks.
Can I just add that old comment? It isn't what you don't know that gets you, it's what you don't know you don't know.
Yeah, right.
Marno, Quintin, would you like to comment on the verification validation questions?
Yep, I'll take a stab. I think first of all, we've gotten accustomed to just plainly accepting whatever an LLM tells us. It's very easy to type something into ChatGPT or whichever provider you use and get an answer and just believe that answer at face value. And it's a very slippery slope and dangerous situation to be in. So my direct comment here would be we cannot purely trust that the AI providers do enough to provide accurate answers. The way in which they train their models is completely, or let's rather say the way in which they provide the models to us is completely divided from the rest of our modeling process. And I think that's what we try to highlight in this last slide as well, is we should take the rigorous approach of being, well, when we do modeling, we should take the rigorous approach and make sure that we validate and verify our whole setup as we go along and not just purely trust that what the AI says is correct. That's the main point I want to bring across. I do not think that there is enough validation that's happening currently out there. There are methods for evaluation of LLM results, so I have seen that. I cannot give you an exact example of that now, but there are actually platforms with which you can test and validate and evaluate your LLM responses or your AI responses then.
Thank you, Quintin. I would also maybe just want to say there that it's not only about artificial intelligence, but even just simulation, because at the conference we had in System Dynamics last year, it was a well-debated point. How do we validate system dynamics models? So that's even without adding the complexity of artificial intelligence. So I think we need a lot of more thinking and maybe publishing or research, like David said, about validation and verification. Any more questions, comments from anyone?
Yeah, I would just like to add to the conversation. Me, who more humbly use quick burst simulations in day-to-day supply chain kind of environment for solving day-to-day problems. There's kind of a stigma that has formed in some way that can you ever trust what the simulation tells you, and it's really placed within this theme. And I always say you need to make it part of your working method. Be aware of it and make sure that you always have, at least pull some kind of real world results that you compare it with, and make sure that whatever the results are, that you sense check it, passes the smell test in quite a few arenas. Because quite often the answer to a lot of the problems that you're solving is maybe not as complex, but the more variability comes into play, the more simulation is required to solve those issues and to solve those things. So I mean, it just needs to be part of your working method for your day-to-day kind of things. In those arenas where it becomes it's more in the world of the uncertain, I guess is what you guys were referring to more often, is what supporting tools can be used to help validate that. For that, unfortunately, I don't have an answer, but so or maybe that should become a new operations research topic to study and get PhDs on. But yeah, that's my 5 cents.
It's been a topic since the 60s. It's not new.
Thanks for that comment, Rion. David, you want to say something?
Yeah, I had one other thought is that there's like a very sort of seems to be a very sort of hard computational limit on what you can do with simulations. Because even when you're doing, like, let's say you're in the logistics game and you're trying to simulate, like, orders over a long period of time, say a month or 6 months, and you can simulate these sort of distributions of orders coming into the system. But how do the decision-making process in the planning phase is itself a very difficult problem. And if you apply like our best techniques to get really accurate planning routines for each and every one of those distributed order streams, it becomes computationally, infeasible. So the interesting thing with simulation is this ability to like sort of smooth down some of the computational complexity to a point where you can do a lot of runs and then hope in all of those runs that you're getting some sort of convergence on like some sort of accurate distribution that you're looking at. But this is where this whole validation thing comes in, because it's really difficult to know if you've done that correctly until you've got some real feedback.
And I guess it really speaks to Quintin's comment of saying that it should remain a decision supporting tool and not necessarily replace those decision making. Because at the end of the day, I mean, for those that have been in a consulting gig, sometimes you go the nth degree of getting it as accurate as possible, but at the end of the day, the CEO will make the decision whatever he wants to make, according to his agenda. So it all just informs, that decision making. At the end of the day, we still need to use our own brains, without being too blunt about it, but as to how to go about it.
If I can chip in again, you remind me of a case study we did, I don't know, 50 years ago, which involved a very radical proposal, which the business executive decided to go with, which involved a fairly large capital expenditure. And while he was signing it, he said, "I hope you've got this right, because it's my name that's going on here, not yours."
It sounds too familiar. Yeah.
I think that also goes with what Quintin and Marno said about responsibilities, and it's also about accountability. We cannot hand over that responsibility and accountability to the model or to a computer or to artificial intelligence. It remains a person that must take that accountability.